2.1 and 2.2, Numerical and Graphical Approaches to the Definition of Limit. Our objectives for today are: you want to develop a conceptual understanding of a limit. You want to understand what it is and also what it isn't. You will estimate a limit by using a table, and you will estimate a limit by using a graph. And vocabulary for today is limit, and again, as a part of your conceptual understanding of what a limit is, you should understand what it is not. What is it not talking about, as well as what it is talking about. So let's take a look at some examples to make this conceptual understanding a reality for you. Today's lesson will consider three closely related functions, f, g, and h. Their similarities will help us understand what is meant by the limit of a function as x approaches a number c, and their differences will help us understand what a limit is not. So what makes these functions closely related? Well, f of x is the linear function x plus 2. But why is g of x closely related to the function f? G of x is closely related to the function f because I'm able to factor the numerator, as I've done here. And when you do that, you can see that there is a common factor of x plus 1 that you can cancel to simplify the function g of x to x plus 2, which seems like it would make g exactly the same as the function f, because the function f is also has the rule x plus 2. But it's not exactly the same, because g of x is actually what you began with. And in what you began with, there is a factor of x minus 1 in the denominator, which makes it different from the function f, because when you consider the original rule for g of x, you've got to say the domain does not include the input value 1, because that would cause division by 0. So g of x is almost exactly the same as f of x, except that it's not defined at x is equal to 1. X cannot be equal to 1. And if you look at h of x, it looks like f of x because it's got the same rule x plus 2 for all values of x not equal to 1, but the difference is when x is equal to 1, the output value from the function h is 0.5, rather than compare that to the function f. When the input value is 1, the output would be 3. So you can see why these three functions are similar to each other, and also you can see why they're different from each other. And we want to work with these three functions to help us understand what is meant by the limit of a function as x approaches a number c. Specifically, we'd like to see what happens as the input value approaches the number 1 for each of our three functions. And the differences between the three functions will help us understand what a limit is not. Because what we will find is that although the three functions have the differences that we just went over, they will all have the same limit as x approaches 1. So that will help us understand what a limit is, and the differences among the functions although will help us understand what a limit is not. Because the differences they don't matter for determining the limit of each function as x approaches 1. So now we're ready to look at our first example for the function f of x, and we want to know what happens to the output values of the function as the input values get closer and closer to 1. And looking at that example will help us have a conceptual understanding of what we mean by limit, and then we will be able to estimate the limit for our example by using a table as well as by looking at the graph. So for number 1, we have the function f of x is equal to x plus 2, and what we want to do is we want to find, and how do you read this notation? You can see that at the bottom of my screen here. This is read as the limit of f of x as x approaches 1 is equal to some value, or maybe none at all, depending on the problem. But in this case, there is a value. And what does this mean? Here's the conceptual understanding that you should have for what is meant by this notation. what is meant by a limit. And that conceptual understanding can be summed up in this sentence. What this means is, as the x values, or the input values, as the input values for the function get closer and closer to 1, the output values get closer and closer to what number? And that number is the limit of the function as x approaches 1. And to help us answer that question, we're going to look at, here we have the function f of x entered into Desmos, and we have a table, and we have a graph, and we want to take a look at that. When you take a look at the table here, you can see that the input values are getting closer and closer to 1. And when the input values are getting closer and closer to 1, the output values are getting closer and closer to 3. That happens as the input values get closer and closer to 1 from values that are less than 1, as well as when the input values get closer and closer to 1 from values that are greater than 1. In either direction, the output values get closer and closer to 3. So we say the limit of the function f as the input values approach 1 is equal to 3. And you can see that graphically as well. So if you look at the graph of f, which is right here, and here on the horizontal axis we have x is equal to 1, and here on the vertical axis we have y is equal to 3. So as the input values get closer and closer to 1, either from the left of 1 or the right of 1, you can see that the graph is getting closer and closer to 3 for y. And this is what we mean by the limit of the function as x approaches 1. So we would say for this problem that the limit of f of x as x approaches 1 is equal to 3. Again, how do we read this notation? We read it like this. The limit of f of x as x approaches 1 is equal to 3. And what does this mean? It means as the input values for the function f get closer and closer to 1, the output values get closer and closer to 3. And we were able to see that from our table of input values getting closer and closer to 1, and the output values were getting closer and closer to 3, whether the input values were getting closer and closer to 1 from the left of 1 or from the right of 1. And you can see here, just as we saw earlier, that you can do this graphically as well. As the input values get closer and closer to 1, the output values get closer and closer to 3. And that is what we mean by the limit. So now we have a conceptual understanding of what a limit is. But we want to look at the other two examples so that we may understand what a limit is not. So if we look at number 2 now, and we look at the function g of x is equal to x squared plus x minus 2 divided by x minus 1, and we want to find the limit of g of x as x approaches 1. Now, what does that mean? Just like we saw with number 1, what this means is, as the input values for the function g get closer and closer to 1, the output values are getting closer and closer to what number? And that's what is meant by the limit. And we read this notation as you see at the very bottom. The limit of g of x as x approaches 1 is equal to. Now, as we noted earlier, you can factor the numerator of the function g of x, and that would make the function g of x equal to x plus 2 times x minus 1 in the numerator divided by x minus 1 in the denominator. And for x values not equal to 1, you may cancel this common factor to simplify the function g of x to be x plus 2, which is the same as the function f, but with one difference. You do have to keep in mind that in the original definition of the function g, you have this factor of x minus 1 in the denominator, which means the function g is not defined for x is equal to 1. So even though you can simplify g of x to be x plus 2, you have to write for all x except x is equal to 1. Okay? For all x except x is equal to 1. Or for x not equal to 1. And you can see from the table that we have for the function g that at x is equal to 1, the function is undefined. And in fact, when you graph the function at x is equal to 1, you should have a gap in the graph or a hole in the graph. It didn't really show up quite well in Desmos, but it should be like that. Perhaps if I didn't do the table, it would have shown up as a hole in Desmos as well. But there should be a gap or a hole at x is equal to 1 in the graph. But does that matter when we're finding the limit? It does not. Because again, what is the limit? It's just a question about what's going on with the output values when the input values get closer and closer to 1. So it doesn't matter that the function is not defined at x is equal to 1. It could be defined or it could be undefined. But when we're thinking about the limit, we're not thinking about what happens with the output value of the function when x is exactly 1. We're thinking about what happens with the output values of the function when the input values get closer and closer to 1. So it really doesn't matter what's going on at x is equal to 1. It matters what's going on for x values that are close to 1. So that's what you need to understand about a limit conceptually. What is it not? It is not what's going on with the function at x is equal to 1. What is it? It is what's going on with the function as the x values approach 1. So what's going on with the function as the x values approach 1? Again, as I just said, it doesn't matter that the function is undefined at x is equal to 1, because when we think about the limit, we're thinking about what's going on as the x values get closer and closer to 1. So when we look at this numerically, we can see that the y values are getting closer and closer to 3 when the x values approach 1 from the left of 1. And when the x values approach 1 from the right of 1, we can see that the y values are also getting closer and closer to 3. So the limit of g of x as x approaches 1 is equal to 3, just as the limit of f of x in our first example as x approached 1 was also equal to 3. So it didn't matter that the second function g of x is undefined at x is equal to 1. It made no difference for the limit, because the limit is what's going on with the output values as the input values approach or get closer to 1, and not what's going on with the output value when the input value is exactly 1. So as we just saw for this problem, the limit of g of x as x approaches 1 is equal to 3. How do you read that? The limit of g of x as x approaches 1 is equal to 3. And what does it mean? It means as the input values for g get closer and closer to 1, the output values get closer and closer to 3. Now we will look at our third example to understand what a limit is and what it is not. Again, we've already seen the function h, so let's look at that. So here we have number 3. Our third function is h of x is equal to x plus 2 when x is not equal to 1, and h of x is equal to 0.5 when x is equal to 1. So you'll see that this is the same rule that we had for our first function, but the difference between this function h and the function f from number 1 is that for number 1, this rule was used for all values of x, and for number 3, for the function h, this rule is used for all values of x not equal to 1, and when the input value is equal to 1, the function is defined to be 0.5. So we'll begin by graphing this function. It's a piecewise defined function. So you can sketch the graph of y is equal to x plus 2, which would have a y-intercept of 2 and a slope of 1. So we would sketch the graph as you see me doing right now. But there is a difference. The difference between the graph from number 1 and the graph for number 3 is there is a gap in the line at x is equal to 1. And the reason for that is you only use the rule x plus 2 for x not equal to 1. So what happens when x is equal to 1? The function h of x is defined to be 0.5, have an output value of 0.5 when the input is 1. So you have a point on the graph of h down here. At x is equal to 1, y would be 0.5. So that's what makes it different from number 1, where the function was just the line y is equal to x plus 2 with no gap in it. And this is also different from number 2, where we had the function g of x, where the graph was the same as this line with the gap at x is equal to 1. But here for number 3, we have the line with the gap, but in addition to that, different from number 2, we also have this point, a single point at x is equal to 1, where y is equal to 0.5. So although we have these differences between the functions for 1, 2, and 3, they all have the same limit. And the reason why I wanted to show you that is because I wanted to help you understand what a limit is not. What is a limit not? What is it not? It is not the output value of the function when the input is exactly equal to 1. It is what's going on with the input values. It is what's going on with the output values as the input values get closer and closer to 1. So here's what we have. So find the limit of h of x as x approaches 1. And again, you look at what's going on with the output values of the function as the input values get closer and closer to 1. So you can look at this graphically, and you can see that as the x values get closer and closer to 1, the y values are getting closer and closer to 3. So you're going to write the limit of h of x as x approaches 1 is equal to 3. The same answer that we had for numbers 1 and 2. The limit of h of x as x approaches 1 is equal to 3. And what does this mean? It means as the input values for h get closer and closer to 1, the output values get closer and closer to 3. That's what you need to understand about what a limit is. It is not asking you to figure out what the output is when the input is exactly 1. So the limit here is not 0.5. It's in fact 3. You can also get that numerically if you made a table. So from this table you can see that as the input values get closer and closer to 1, either from the left of 1 or from the right of 1, the output values are getting closer and closer to 3. Again, it does not matter that when the input is exactly 1, the output is 0.5. That's not what we're considering when we think about the limit. What are we considering? We're considering this. As the input values for h get closer and closer to 1, the output values get closer and closer to 3. So the limit here is 3. The limit of h of x as x approaches 1 is equal to 3. So the 3 examples that we looked at today should help you conceptually understand what a limit is, and especially what a limit is not. With that being said, I would like to make one point about what we've been talking about in 1, 2, and 3. So in this example for number 3, the limit is equal to 3. It is not equal to the output value of the function when the input is 1. In fact, the output value of the function when the input is 1 is 0.5. In number 2, the limit of the function g of x as x approaches 1 is equal to 3. It did not matter that the function g of x was not defined at x is equal to 1. In our first example, the limit of the function as x approaches 1 was equal to 3, and it happened to be equal to the output value of the function at the input 1. It happened to be the case. When would that coincidence occur? That coincidence would occur when you have a function that is continuous at whatever value that we're taking the limit. And we'll learn more about that later, but just keep that in mind. But for today, keep in mind, it really doesn't matter that this happens to be 3. That is not a requirement, and that is not what we're talking about when we consider the limit. But when we do have a continuous function at x is equal to whatever value we're taking the limit, that coincidence would have that convergence of the two values. The limit as f of x as x approaches 1 is equal to 3, and it also happens to be the case that the function's output value at 1 is equal to 3. So we'll talk more about that later when we talk about continuity, but for today, remember, this doesn't really matter, as we saw with numbers 2 and 3. So for today, we focused on numerical and graphical approaches to the definition of limit, and the objectives for today's lesson were for you to develop a conceptual understanding of a limit, and we estimated limits by using tables and graphs. And in today's lesson, we considered 3 closely related functions. Their similarities helped us to understand what is meant by the limit of a function as x approaches a number c, and their differences helped us to understand what a limit is not.